Okay, kiddos, as promised, I'm going to make another video for you related to colligative properties. We're going to do one where we're going to find the molecular weight of an unknown compound, and we're going to do that by freezing point depression. That'll be our first problem. And the second, we're just going to find the freezing points and boiling points of a solution solution made up of this solute dissolved in water. So that'll be the second example that we do. Okay, so here we go. A 0.0355 gram sample of an unknown compound. It's molecular, so it's non-ionic, kiddos. It's dissolved in 1 gram of liquid camphor. This solution freezes at 157.7 degrees Celsius, so a pretty high freezing point. I want to find the molecular weight of the unknown. Now for that, you need to know the normal freezing point of camphor, which I've given, and the freezing point constant. So if you remember, there are two things you need to know to find molecular weight. Do you remember what they are? That's right, the grams and the number of moles. Now which one of those two is always given to you? That's right, in this case the grams of solute are given. You just have to read the problem, and it's right there. 0.0355 grams of my sample. Now I'm not going to use the 1 gram of my camphor because that's my solvent. I want to find the molecular weight of my solute. So the only other thing I have to find are the number of moles of solute. Now to do that, we're going to use freezing point depression. So if you remember, delta T sub Fp equals K sub Fp times the molality. Now we're going to solve that for the molality because you remember the unit molality is moles of solute per kilogram of solvent, and we want that moles of solute. So the molality would be equal to, let's see, delta T sub Fp over Kfp, if I've done my math right. And so my delta T, let's see, wouldn't that be the difference between the normal freezing point, 179.0, and the freezing point of my solution, 157.7, whatever that difference is in degrees Celsius. And we're going to divide that by the Kfp, which is 40.0 degrees Celsius per mole solution. So let's do that on our calculators. Celsius will divide out and we'll be left with molality. So 179.0 minus 157.7. Now that gives me a freezing point change of 21.3 degrees Celsius. Now we're going to divide that by the freezing point constant, 40.0. And we get to three significant figures, 0.533 molal. Now that's not my number of moles. I don't put that there. Remember, my molality, 0.533 molality units, is moles of solute per kilogram of solvent. Now in this case, folks, my solvent is camphor. So I need to multiply that by the kilograms of camphor. Now this one's a bit tricky in that I give you 1 gram of camphor. Isn't that 0.001000 kilograms? Yeah, we have to convert that grams to kilograms. So let's see what we get. 0.533 times 0.001000 gives me 5.33 times 10 to the negative 4th moles of my solute. And that's the number that I want to put right there. Okay, so 5.33 times 10 to the negative 4th moles. So let's see what our molecular weight turns out to be. 0.0355 divided by 5.33 times 10 to the negative 4th gives me 66.7 grams per mole. So I found my molecular weight of my unknown by how much it depressed the freezing point of my solvent. Did that help? I hope it did. All right, let's do one that might be a little easier. This one's just finding the freezing and boiling points of a water solution after I've dissolved a non-ionic solute in it. So, dissolving 645 grams of urea, H2NCO and H2, and I'm dissolving it in 980 grams of water. So to find the freezing point, folks, it's delta T sub Fp equals KFP times the molality. Now, my KFP is 1.86 degrees Celsius per molal, and I need to multiply this by the molality. I haven't found the molality yet, have I? Nope, I need to do that. So I have 645 grams of H2NCO, NH2, and I needed to go from grams of that stuff, H2NCO, NH2, to moles, H2NCO, NH2. Put a 1 by mole, and I gave you the molecular weight, 60.07 grams per mole. So grams divides out, and I want molality, remember, so I need to divide that by kilograms of solvent, which would be 0.980 kilograms of water. So let's see what we get. 645 divided by 60.07 divided by 0.980 to three significant figures gives me a molality of, 10.9, that would be 11.0 molal units. So that's what I want to put in right here to find my freezing point change, 11.0. So my freezing point change will be 1.86 times that number, which gives me a freezing point change of 20.4 degrees Celsius. So remember, water normally freezes at 0, and this is freezing point depression, so I'm going to drop it by 20.4 degrees Celsius. So my new freezing point would be negative 20.4 degrees Celsius. What would my new boiling point be? Let's do the same thing. Delta T sub Bp equals KBP times the molality. Now my boiling point constant for water is 0.512 degrees Celsius per molal. And I'll multiply this by my molality, 11.0, and I will get my boiling point elevation in degrees Celsius. So 0.512 times 11.0 is 5.63 degrees Celsius. Now water normally boils at 100 degrees Celsius. Its boiling point elevation, so I'm going to add 5.63 degrees Celsius to that. So I end up with 105.63 degrees Celsius for my new boiling point. Okay, so you can see the freezing point's dropped, and the boiling point has risen. It's been elevated. Okay, hopefully that helps clear a few things up for you. I know you're probably struggling on those, so there's two more examples for you. You're welcome. See you soon. Bye-bye.